Okay, let's turn next to the problem set. And so here problem 1 is you want to find out whether there's a difference between male and female littering behavior. And for this purpose, you collected the following data that you summarized in a crosstab. You can see I have opened Excel because we can just copy this data quickly and then paste it into Excel. And then maybe we want to fit to content. Okay, so this is our data, and we want to test the hypothesis. The null hypothesis is that there is no gender difference in littering behavior. The alternative is that there is one. And we want to test that at an alpha of 5%. Okay, so the first step, what we need to do is let's complete the table and get the column totals and the row totals. So we have a total of 25 females, a total of 75 males, 60 deposited, and 40 were litter bugs. So that's a total of 100. Okay, so let me highlight those inner cells because those are the ones that matter later when we talk about degrees of freedom. So what we have here, this is the actual behavior. So the question is, what is actually the expected behavior? So let's just copy this entire crosstab and let's put it underneath. So now we want to know what are the expected. So how can we infer that from our actual crosstab? Well, the expected number of observations, they can be derived from the assumption of independent events. So if we assume that gender and littering behavior are truly independent, then we would say, for example, for females and depositing, if we assume that this is completely independent, then we would expect that the probability of randomly selecting females that deposit, but if there are independent events, that would be the probability of being female and a depositor. Okay, so this would be equal to the probability that someone is a female, so that is the 25 over 100. So it's 25 over 100. So it's basically this cell over 100 times 60 over 100. Okay, and what that is, that would be, for example, so this would be equal to 1,500. 100 times 100, that's 10,000. So that would be 0.15 or 15%. But what we need to do is we need to take this 15%, so 25 times 100 times 16 times 100, that is 15%, and we have to multiply the times the 100, and then we get the expected frequency under independent events. So that means that here we would expect 15. And of course the shortcut is, because this is the formula that we apply, which is this times this, and each one over the 100, but then again times 100, so that means that cancels out, and I can get the 15 simply by saying, okay, this is the 60 times the 25 divided by 100, and then we have the 15. Then likewise we would say, what's the expected frequency for females at litter if we assume independence? Well, then we would use 40 times 25 divided by 100. Then depositing and being a male, that would be equal to the 60 times 75 over 100, 45, and males and littering under the assumption of independent, that would be the probability that a randomly selected person is a person who litters, and the probability that a randomly selected person is a male divided by the 100, and we get 30. Okay, so this is how we could calculate it, but of course once we calculated just one, we know what the others must be, and that is related to the concept of degrees of freedom. So here, once we know one cell, among those 4 cells we know all the other. We know that 15 plus the blank must be 25, so it must be 10. Then vertically 15 plus what must be 60, well that's the 45. And 10 plus the blank is equal to 40, well that's 30. So now we know that the degrees of freedom for a crosstab in this particular case is 1. But the general formula is that the degrees of freedom is equal to the number of rows that we have minus 1 times the number of columns that we have minus 1. So here we have 2 rows and 2 columns. So this is 2 minus 1 times 2 minus 1, which is 1. So we have 1 degree of freedom here. Okay. So we have 1 degree of freedom. And now what we can do next is we can actually calculate the chi-squared statistic. So for this purpose, I just copy again the table and paste it below. And here we calculate the chi-squared. So we don't need the border here, actually I can delete that. So here we calculate the sum of expected minus actual squared divided by expected. So let's fit to content again. Okay. So now we just can use the formula. So for the first event, which is female, and depositing, we have an actual observation of 18. So the difference to the expected is 3. So 18 minus 15, that's the 3. Then we square everything, and then we divide by the expected 15. Okay, here we get 0.6, and now I can copy that formula to the right. Control R copies to the right, and now I can copy down both, which is Control D. So now the sum of those 4 cells that I just calculated, that is our chi-square test stat. And that is equal to the sum of those 4 values, which is 2. Okay, so now this is our test statistic. And what we try to do is we have also a critical test statistic, and it actually turns out that the chi-squared distribution looks something like this. So it starts at 0 and typically looks something like this. So now what we try to find is the critical chi, which is the one at which we would reject at an alpha of 5%. So that is chi critical. So what is that? So we can calculate that as chi critical. So we can use the Excel formula equals chi, and then there is something called chi squared dot inverse right tail. And here we can say we need it for the probability of 0.05. And then Excel wants to know how many degrees of freedom do we have. Well, we know we have 1. And that means that our critical T is something like 3.8. But we can clearly see that the 2 is inside, so we fail to reject. So we fail to reject. Okay. So we still want to know what's actually the probability of getting something which has a chi-squared statistic of 2 when we have 1 degrees of freedom, and we can still calculate the p-value. And so that p-value will then just tell us the probability of obtaining what we see here if there's presumably no difference. So that is then the p-value. And the formula for that is equal chi, and now we use the formula chi-squared dist RT, and that gives us the probability to the right of 2, which must be greater than 5%. And again, we have 1 degree of freedom. And it's 15%. So So there's actually a pretty big chance that we can find 18 females who deposit and 7 litter when there are like 25 females, and when there are also 42 males who deposit but 33 who litter. There is still there's a chance that this observation, this actual observation, comes from a scenario where there's actually no difference between the two. So there's one other thing I just want to show you. I want to show you what the chi-square distribution looks like. And so I do that quickly in a separate sheet. So I'll just create a chi. I start at 0 and I'll just create a column that has a step value of, let's say, 0.1 and ends at 20. And then I'll make the degrees of freedom a variable, but here we have currently 1. Okay. And yeah, so what is then the probability density function? So for this purpose we use the command chi, and there's something chi-square distribution returns the left tail probability. Okay, so 0 degrees of freedom I pick up from here, where I made it a variable, and then I just say F4. And now I don't want it cumulatively. I don't want the area, I want the actual probability value on the y-axis, but not the integral. I don't want the area under the curve. So 0. Okay, so that's fine. For 0 there is no chi-squared, so we make that an NA for the 0. And so now let's see what it looks like. Highlight everything, insert, recommended chart. Yeah, it actually looks like more like this. And so let's put that maybe quickly here. But you see, if I change the degrees of freedom to, for example, 2, the curve starts to change. Degrees of freedom 3, 4, 5, 6. And if you have many degrees of freedom, like 100, well, then it also looks not good for our range of x-axis. Let's say 10. You see it approaches ultimately also the normal distribution, but let's go back to 1. And if we want to, we can add now to our graph the test statistic and the actual critical value. But yeah, I don't think we need to do that and encode that now. So I think that should be pretty clear. So it's the same spirit that we always pursue whenever we do a hypothesis test. So we always assume there's no difference between anything, but then we look at our actual observations, and we ultimately ask the question, what's the probability that what we see in front of ourselves comes from a scenario where there's no difference? Okay, so but let's go back and let's work on the next problem set, but let me quickly add here 25, 75, 100, 60, and 40. And so what is the result? So we reject, we fail to reject the null, because our test stat of 2 is less than our critical test stat of 3.84. Okay, so now let's move to another problem set. And here it says this question is the second part of the video. Yeah, I don't really remember anymore what video that is. But here a company created flyers in different colors and wants to know whether there's a difference in creating attention. So now we have a different scenario where we have more columns, and we can do that a little bit faster now. Okay, first thing we do is we create again the total. So we are like a total of, the sum is 90 took it, and $60 didn't. So again, the question is, a company created flyers in different colors and wants to know whether there's a difference in creating attention in terms of being picked up. Below is the cross tab with your observations. Okay, so how many white ones did we have? That's 40. How many light blue? That's 60. And how many neon pink? Well, that's 50. So we have a total of 150. Okay, so next we copy and paste this cross tab again. And so on top we see the actual observations, and now we need to calculate again the expected. So now we have 2 rows. And we have 3 columns. So that means now we have 2 degrees of freedom. Because degrees of freedom is number of columns minus 1, 1, 2, 3, minus 1, that's 2. How many rows? 1, 2. So 2 times 1, that's 2. And so what is again the expected? So the expected, I just enter that manually again, 90 and 60. Okay, so now what we can do is we can also just calculate it quickly, saying, well, this first cell, which is take and the white, is the frequency of the white times the frequency of the take divided by the total. Okay, so now I can also copy that formula. So B10, what I want to prevent is that when I copy down that formula, that it moves down. So I can put in front of the row a $, but not in front of the B, because I want to copy that formula to the right, so the 40 must move to the 60 and to the 50. As for the 90, I need to put a $, in front of the E, because I want to copy down this formula, but I don't want it to shift to the right. And divided over the E10, I need to put a $, in front of the E and the 10. And now we see that the expected frequency for taken white would be 24. And again, we apply the formula for independent events. And Arjun can copy that to the right. And you see that the sum 30 plus 36 is 66 plus 24, 70, 90. So that is a useful shortcut whenever you work with such data in Excel. And you also see that if I had any two combinations, then I could easily fill out the rest. So, but I leave it up to you to play around with it. But we just need to fill up the column totals and the row totals. Okay, so the final step is that we take our cross tab again, and copy it into an underneath, and now we create again the chi-squared. Let's just do it like this. So now we use again the formula that we compare the actual, and we subtract from the actual the expected, close parentheses, square it, and divide by the expected. And now I can copy that to the right, and I can copy it down. And then I have many decimals here. So now we have again our test chi, our test statistic, which is again the sum of all those squared deviations over the expected value. And we get a value of 15.28. How many degrees of freedom do we have? We said 2. So what is our critical chi? Our critical chi would be equal to, so we use the formula chi squared inverse right-tailed, probability 0.05, degrees of freedom 2. And now we get basically a value of 5.99, or close to 6 when we round it. And what we see is that our test chi, which is 15.28, is very, very far in the rejection zone. So now we would have something like this. So our distribution looks like this. And our test statistic is around 15. You see that would be somewhere here. Well, that's not really 15, I guess, so somewhere here maybe. But our critical value is around 6, so that would be maybe here, clearly in the rejection zone. So Okay. But we could have made a type 1 error. Well, it could be that the color doesn't really make a difference whether people take it or not. So what is the probability that we made a type 1 error? And that is, of course, the area to the right of the 15.28. And that's probably very, very small. So now we can say the p-value is equal to, and the formula that you want to use now is again chi-squared distribution right tail. And then you click onto the 15.28. And how many degrees of freedom do you have? 2. So now we should get something which is very, very small, 0.0004. So it seems that the probability that we made a type 1 error is really very, very small. Well, so I hope the intuition is clear. So first of all, let's quickly answer this one. So the answer is so we reject the null because our test stat of 15.28, our test chi stat, is greater than the critical chi of 5.99, but we could have made a type 1 error of, I don't know, 0.04%. Well, 0.05%. Okay, so this is like maybe the cumbersome way of conducting a chi-square test, but there's also the shortcut. So Excel doesn't have normally whenever we work with a hypothesis test, we went to data analysis, and we did our hypothesis tests there. When you browse through those options under the analysis tool, there's nothing really for a chi-square test. And the reason is that it's just a formula that you can use in any cell. And the formula is chi-squared dot test. And then it just wants to know what is the actual range. So now we have to highlight those 3 columns and 2 rows. You don't highlight the border with all the totals. And then you highlight similarly the expected output. And then Excel is smart enough to calculate the degrees of freedom, so we don't have to enter that. We just close the parentheses and we enter it. And now you see we get the p-value, which is the same that we just calculated. So the chi-square test just gives you the p-value. If you want to know the corresponding test statistic, the 15.28, then you just can reverse engineer the p-value, and you use again the command chi squared, and then so now we have to use the so it's actually chi-squared dist returns the left-tailed probability. We don't need a probability, so we need a chi-squared inf. Right tail returns the inverse of the right tail of the chi-squared distribution. So, and the probability we pick up from here, and again degrees of freedom is 2, and then we see the 15.28 here. Okay, so in other words, the chi-squared test doesn't automatically report the actual test chi statistic, but only the probability of the test, but you can easily reverse engineer it from the probability using the command chi-squared.inverse.rightTail. Okay, so in summary, in the first one, we failed to reject, but in the second example, we rejected the null. And here, in the first example, we failed to reject. Okay, so let's just stop here, and then we just continue with another problem set in the next video. Okay, so I'll see you there, hopefully.